Hello everyone, this is my EWB independent project where I looked into the feasibility of biochar filters in Malawi. I'm sorry I couldn't make it. Fortunately, have a physics midterm at the same time. Wish me luck, guys. And this is just some of the research I did and some of the findings I want to present here. So the first paper I looked at talked about the occurrence of contaminants in drinking water sources and the potential of biochar to improve water quality. And it's basically a large review paper that looked at various sources and compiled the main findings of how they use biochar in water quality. So the first graphic I want to show here just shows the biochar can either be just used as it is, or it can also be modified, and through these modifications it can trap certain contaminants, so things like endocrine disrupting chemicals and personal care cosmetic chemicals, organic matter, heavy metals, and microbial contaminants, which is what we're interested in. And biochar can be used therefore to filter and produce clean water. So first I want to talk about the different contaminants. The US EPA and WHO have set strict standards for most of the contaminants, except for PPCPs and EDCs, which are like personal, I think these are personal cosmetics chemicals, as well as pharmaceutical chemicals. And then EDC are endocrine disrupting chemicals. These are not really monitored. And then there's also other chemicals known as odorants, which are not as well known, and these are difficult to locate and identify, and they're usually categorized by a number of 3. And then this chart here just shows the different chemicals and kind of their set standard levels that we should keep in mind, and this is probably most important for E. coli and something we can keep in mind when we're testing how the biochar works. So this table kind of continues on and shows the different contaminants and where they are found. So for example, nitrate and nitrite are found often in fertilizers and industrial waste, and this talks about like if there's a source of turbidity, which is the water is not really clear looking, it's usually due to soil erosion or even algal growth, and then odor can be due to microbial stuff. So it just shows kind of the different source of contaminants. Next, I'm going to go into how biochar works. So there's 2 types of biochar. There's modified and there's pristine biochar. Modified biochar is when you take the biochar and actually do chemical or physical modifications to it. So this includes treating it with acids, bases, organic compounds, or mineral oxide, whereas pristine biochar is just changing the temperature at which you heat it up, for example. So these are some examples of how modified biochar can be used. So in this example, in order to remove, like dechlorinate this chemical called trichloroethylene, one group used a biochar made from wheat straw, as well as this kind of biological compound, and they were able to degrade it to 99%, which is pretty good. This chart here just shows how biochar works. It basically works through adsorption. So there's your biochar, and then these are all of your contaminants, and they basically just stick onto the biochar. And something else that was really important to note was that, like I kept saying before, different contaminants influence the type of biochar, and it's really important to note that for some contaminants, just the regular biochar isn't going to help. Luckily for E. coli, we can actually use the unmodified biochar. We don't have to make any major modifications to it, and I'll explain that in another table. This just shows like the mechanism for biochar. I'm not going to get too much into it. So this is for like organic compounds, which is your E. coli, your viruses, and then these are like your inorganic compounds, like your heavy metals. And this just says that the pH of the solution must also be considered, because that can affect how effective the biochar is, or how much biochar concentration you need in order to remove those compounds. And this also shows that biochar mainly has this absorption quality through its negatively charged and polar functional groups. And you can see a lot of those polar interactions happening here. This is talking more about inorganic contaminants and kind of the specific type of biochar modification that would be best for this. So I just want to note that here you can see that using the same type of biochar but at a 7 pH versus a 3 pH increases the efficiency. Just going back to the point where pH of the solution impacts the efficiency of biochar. This here kind of shows that even though we increased the temperature of biochar, it's still like the iron biochar, 25 degrees Celsius, showed more than 99% removal efficiency compared to pine sawdust biochar at 300 degrees Celsius or at 550 degrees Celsius. It just shows that heating the biochar doesn't necessarily mean it'll work better. You really have to consider for a lot of these different contaminants the modifications you make. This is the table I was talking about earlier. So this table just shows kind of the best as well as the worst biochar for E. coli. So you can see the worst one at 27% would be your waste wood pellets, and then the greatest efficiency ones would be your forestry wood waste biochar. But a lot of these other ones also work really well, like the softwood works really well. And then the hard and soft wood with almost like a 98 to 99% efficiency. So this just shows you don't really need crazy modifications for the biochar in order for it to filter out the E. coli, which is pretty good for us. So some other things that this paper noted were that biochar with sand was really recommended, and using biofilters like fairly column filters with biochar is recommended. And the mechanism for E. coli and biochar, like how biochar is able to filter out E. coli, is pretty complex. There are a lot of different things that are proposed in different papers, like hydrophobic attractions or the electrostatic attractions between the gram-negative and the different compounds on the biochar. So I'm not going to get too into that. This slide talks about the benefits and the risks of biochar. So the benefits are that it's pretty environmentally friendly, as we all know. It definitely reduces greenhouse gas emissions, and it is really good at what it's supposed to do. So it's able to just hold on to those contaminants and not let them seep through. But there are some risks. During the pyrolysis process, which is essentially the process where biochar is made by heating organic material without oxygen, it can turn into volatile organic compounds or polycyclic aromatic hydrocarbons, among other things, and these can have negative health effects. So it's just something to keep in mind when it's actually being made. The next thing that the paper talks about is kind of upscaling. So now that you want to use biochar, how do you go about it? This is like a proposed filter they have, which I think would be especially helpful to implement in our own filtration, in our own prototype systems. And I think we already use some of it. So they recommend using gravel, which we already use, fine sand. With biochar, you can either use kind of the regular biochar, or you can do some sort of modifications, and using this with a column filter. So the steps that the paper recommends us to follow is first kind of just selecting your appropriate feedstock. That just means what type of organic material you're going to use to make the biochar, and then also figuring out what temperature should be heated at. Is there going to be benefits of preparing it one way over the other? Do we need any modifications? And then how can we implement it into a larger system? So obviously biochar by itself isn't going to remove everything, and so you need to include it with other water-based water treatment systems. So now I'm going to talk about previous large-scale projects that was mentioned both in paper, and these images I just Googled them and found them. So this one is really interesting. This is, I think, the most similar to what we're doing right now, and this was in Southeast Asia, where they basically prepared biochar in 200-liter drums. And it can treat about 113,000 liters of water per day. So you can see they have these multi-barrel systems, which is pretty interesting. And I would be interested in seeing kind of how this system would compare to more of like a column filter where everything is in a single column. This is another biochar-based filtration system used to remove arsenic from groundwater, and this was done in Mexico. So you can see here, this I believe includes more electrical components, and it has like more advanced filtration systems included in it. And then this here just talks about different water filtration systems and just, compares between them. So what I just want to highlight is filtration is really effective, especially filtration made from wood biochar or H2SO4 modified biochar, and they're easy to implement. And that's what the paper really emphasized. The paper also mentioned chlorination, which I think we used previously, like in our own like Malawi project. But chlorination, while it's really effective against infectious diseases, it can produce disinfection byproducts, which have some health risks associated with them. So next I'm going to move on to the second paper, which talks about the gasification of biomass as an alternative energy source to fuel wood and charcoal, and it's a feasibility study in Malawi. So first, this paper starts by introducing a little bit about Malawi. So Malawi has a population of around 13.5 million people, not billion, and a large percent of the GDP and labor force is involved in agriculture. While there are existing sustainable farming practices, there are still some, poor practices like burning crop residues, lack of fertilizers, floods, and by encouraging the use of biochar, we can encourage these farmers to use their pre-existing crop residues. And another big problem in Malawi, at least around the time that this paper was written, is the deforestation, as well as the charcoal production, like just the heavy reliance on biofuels. At this point of the paper, like when it was written, this paper was pretty old. It was, I think, around 2010 when it was written. There was a company called the Energy Supply Corporation of Malawi, and they're trying to increase the amount of electricity people use and kind of decrease the reliance on biofuels. So just checking up and seeing what the progress is on that would be interesting. And obviously deforestation is bad. We want to prevent deforestation because it can reduce the amount of water in groundwater and rivers, which can also not only just negatively impact soils, but also impact the amount of drinking water we have. So this is going into more of the chemistry behind it, the theory behind it. So in this paper, they talked a lot about this process called gasification, which I will talk a little bit more about. But basically, there's three components to this system. They have pyrolysis, which uses low amount of oxygen, and then complete combustion, which uses a high amount of oxygen, and then gasification, which is somewhere in between. And this system not only produces biochar, but can also produce like electricity or gases that can be used as resources. So there are two types of pyrolysis this paper talks about. The first one is fast pyrolysis, where the biomass is heated really quickly, and slow pyrolysis, which I believe is more effective for the biomass for the water management, where it's kind of obviously it's heated slower, and it's heated at much smaller quantities. And then the other thing this paper talks about is these things called ash elements like sodium, potassium, magnesium, and silicon, which take energy from the combustion process and can cause problems in the systems. So of really important note, which I found really interesting, was the types of charcoal kilns they talked about. So here we have an earth mound kiln, which is easy to build, but it's really not that efficient, and it doesn't really have oxygen control, so you can't really control the pyrolysis, and you can't really control the quality of the biochar being made. Next, you have a brick kiln, which looks kind of like this, and while it can be reused, again, you can't really store the gas, which you want to use for as like another resource, or also you don't want the gas to just being emitted because that can contribute to greenhouse gases. Here you have a retort kiln, which reduces emissions, and then by a lot. And then here you have a wood gas stove, which is what this paper recommended, and it uses slow pyrolysis, which again is probably going to be what we use for drinking water management, and it has kind of zones where there's both a pyrolysis zone as well as a combustion zone. The greenhouse gases are highly reduced, up to 90%, and it also can produce biochar. So this is the Peko Pay stove. I'm definitely pronouncing that wrong. It is a type of wood gas stove, and it's the wood gas stove that they used in Malawi in order to produce biochar. And this is kind of some of the statistics behind it. So it's made out of stainless steel. It creates biochar that is 25% of the original mass. And some of the disadvantages of the Peko Pay stove is that it is slow because it works batch-wise, so it can't produce a large amount of biochar at once. And it's also just the biggest challenges are just the price of it, and it needs the fuel. And the fuel that it needs has to be collected, processed, and stored for a long time. So this just talks about the gasifier, and what this paper proposed is that a gasifier can be used in order to convert like energy into biochar as well as into pellets and electricity. So it kind of has a multi-system purpose, and it goes into a lot of depth on how to construct this gasifier and the different types, which I'm not really going to get into, but it's something we can consider and do future research on. So finally, the future directions from the paper, they mentioned how they wanted to redesign the stove in local materials, so the wood stove that I was talking about earlier that can be used to make biochar. Also to initiate a pilot program with selected farmers to create biochar, as well as the gasifying unit, and then design and identifying an oven for biochar production. So again, kind of improving the design of this stove, and conducting field days to exhibit the benefits of biochar. And this paper really focused on using biochar for soil quality, but a lot of this can be extended to water quality. Like something that I took away from this paper was that biochar has like increased ability to store nutrients, and obviously that's important for soil because you want the plants to get those nutrients, but for water quality management you also want the biochar to hold on to excess nutrients, and you don't want that to seep into the water. Overall, what this paper showed was that if we are going to consider biochar, we need to make sure that the biochar we make minimizes the deforestation, so minimizes the tree wood used, and instead uses more of the crop residues. And that's pretty much it. Feel free to email any questions. My email is meghna, meghna, @udel.edu.